Welcome to the Deep Dive, where we unpack complex ideas and make them, well, digestible. Today, we're taking a deep dive into the fascinating world of geometry, but maybe not as you remember it from school. We're drawing our insights from Felix Klein's really profound work, Elementary Mathematics, from a Higher Standpoint, Volume 2.
Yeah, and this isn't just another textbook. Klein's work, it's foundational. It properly reshaped how mathematicians view geometry. He really emphasizes its dynamic nature, and the surprising power of abstraction. It offers this comprehensive vision of the field that he thought every teacher should grasp.
Right. So our mission today is to unpack Klein's revolutionary ideas. We're going to explore, well, everything from the unifying power of transformations to the unexpected insights you get from using signed quantities and even imaginary numbers.
And we'll also dig into his, let's say, sharp critique of traditional geometry education and his vision for how mathematics should be taught. It's quite inspiring, actually.
So get ready to see geometry not as static shapes on a page, but as this fluid, interconnected landscape.
Okay, let's unpack this. Klein immediately sets the stage with a big idea he calls fusion.
Yeah.
He's aiming to give teachers this comprehensive view of geometry, right? He actually puts off talking about how to teach until later.
Exactly. And this fusion philosophy is absolutely central. It's about breaking down those, artificial divisions we often create in math. Klein says we should treat arithmetic, algebra, analysis, geometry, not as separate silos, but as interconnected fields.
Interconnected? How so?
Well, like treating plane and space geometry together.
Yes.
That often gets shortchanged in education, which kind of hinders our natural feel for 3D space.
Yeah.
He also believed in making abstract discussions more alive, with figures, with graphic methods, always connecting that vital space intuition with precise analytic formulas. Basically, let's look at corresponding things on a line, in a plane, in space, using coordinate systems right from the start. Okay, here's where it gets really interesting for me. Klein talks about something seemingly simple, but wow, profoundly powerful: signed quantities. He's saying we should use the signs that formulas naturally give us for things like line segments, areas, volumes.
It's a total game changer. Think about a line segment. The sign tells you the order of the points. So A to B is, say, positive, B to A, negative. And this isn't just neat bookkeeping. It lets complex formulas hold universally. It basically obliterates the need for all those tedious case-by-case proofs you see in older geometry.
Okay, I think I get the line segment thing. But for something like a triangle's area, how does a sign work there?
Right. For a triangle's area, the sign depends on the direction you travel around its vertices. Go counterclockwise, you get a positive area. Go clockwise, it's negative. And this means a formula for the area of a triangle, let's call it 1, 2, 3, with some other point, say 0, it can always be written as the sum of the signed areas of the smaller triangles. 0, 2, 3 plus 0, 3 plus 0 plus 0, 1, 2.
Always, regardless of where point 0 is, inside or outside.
Always. It proves the theorem for all possible positions in one go. It's incredibly powerful, way more efficient.
So this isn't just theoretical number crunching. It has real-world applications. Klein mentions Amsler's polar planimeter from 1854, an ingenious device for finding areas.
Indeed, and its theoretical basis is precisely this idea of signed areas. You can imagine it tracing the boundary of a shape, summing up tiny directed bits of area as it moves. It calculates the net area enclosed. It's a physical manifestation of the concept. And it shows how these fundamental ideas, signed quantities, fusion, they pave the way for understanding geometry through transformations. This new precision with signs, it feels like a really crucial step toward that more fluid, interconnected view Klein was aiming for. No more bumping into exceptions.
Signed quantities give us this amazing precision, making formulas universally true. But Klein takes it further. He argues the real dynamism, the true life of geometry, is in how shapes transform. What's he getting at there?
What he means is that geometric properties are essentially those things you can express in formulas that stay the same invariant under specific coordinate changes. This core idea lets us classify different kinds of geometries based on which group of transformations keeps their properties intact. It's like finding the essential DNA of a shape, no matter how you stretch or move it, within certain rules.
That makes sense. And what about this historical split between analytic and synthetic geometry? It sounds simple formulas versus figures. But Klein suggests it's more complex. Was there a bias? Why did he want to bridge that gap?
Yeah, it's nuanced. Originally, analysis was like general to specific, and synthesis was specific to general, like in chemistry still. But in higher math, the meanings kind of flipped, bizarrely. Synthetic geometry became about figures without formulas, and analytic geometry always used formulas and coordinates. Klein was really passionate about a balanced approach. He argued, look, analytic geometry without pictures is barely geometry, right? And synthetic geometry won't get very far without the precision of formulas. They need each other. They're complementary.
Okay, we've touched on how transformations classify geometries. Can you give us a solid example, like a major geometry Klein looked at this way, and what makes it unique?
Absolutely. Let's talk about projective geometry. What's really cool here is the principle of duality.
Hmm.
Imagine you have a geometric theorem about points and lines. Now, if you swap every instance of point for line and line for point and adjust related concepts, you often get another true theorem. It's wild, like Blaise Pascal's theorem about hexagons inscribed in a conic section. It dualizes perfectly into Charles Bryan-Tone's theorem about hexagons circumscribed around a conic section. Points become lines, lines become points. It's this beautiful symmetry.
Wow. And projective transformations themselves, they're called collineations because they keep lines straight. But here's the kicker you mentioned. They don't necessarily preserve parallelism. How does that work?
That's the mind bender. Unlike affine transformations, which do keep parallel lines parallel, projective ones can take what we think of as the infinitely distant plane in one space and map it onto a perfectly normal finite plane in another space. So lines that were parallel before the transformation, they can now meet at a finite point after it. It completely changes the perspective.
So projective transformations mess with parallel lines.
Hmm.
What other weird stuff can they do? Can they, I don't know, turn a parabola into a circle?
Okay, this is where it gets really wild. Under projective transformations, yes, any two conic sections, ellipse, parabola, hyperbola, can be transformed into each other. And because they can all be transformed into each other, they can all be transformed into a simple circle. From this higher standpoint, the differences we see between ellipses, parabolas, hyperbolas are just, well, accidental positions, different views of the same fundamental object. Projectively, there's only one conic section.
Unifying, to say the least.
It really is. And a key number that stays the same and invariant under these transformations is the cross ratio of 4 points on a line, or 4 lines passing through a point. It's a powerful tag for projective identity.
And you mentioned photography as an example. Central projection. It's a special projective transformation where the determinant vanishes. What does vanishing determinant mean in plain English?
Think of it like this. When the determinant vanishes, the transformation is essentially squashing things down. It's reducing dimensions, like a 3D scene getting flattened onto a 2D photo, or a 3D object drawn flat in a technical diagram. That's a vanishing determinant in action.
Got it. So contrasting that, you have graffiti transformations. These do preserve parallelism.
Exactly. They're less wild in that sense. Parallel lines stay parallel. A great example is axonometric mapping, that parallel projection used in technical drawings to represent 3D objects on a 2D plane. That's an affine transformation, also with a vanishing determinant because it flattens space onto a plane. It explains why, for instance, a sphere under parallel projection always looks like an ellipse, never anything else. And this ties into Polsky's theorem, which basically says you can represent the 3 axes of 3D space with any 3 vectors you draw in a 2D plane using this kind of mapping.
Okay, then Klein moves to higher point transformations. So unlike the previous ones that kept lines straight, these are even stranger mappings. What do they do?
You got it. They're quite different. A key example is inversion, or transformation by reciprocal radii. Now, remember how projective transformations mapped the infinitely distant stuff into a whole plane? Inversion maps the entire infinitely distant part of space into just a single point, the origin.
Just one point.
Just one point. This unique feature makes the transformation perfectly reversible without exceptions. There's no infinitely distant plane anymore, just an infinitely distant point. You see applications in things like geographical map projections related to Tissot's theorems.
Okay, and then he gets into what we now call topology.
Right. He calls it biunique continuous point transformations, the subject of analysis situs. This is all about properties that don't change even if you stretch or bend the shape, as long as you don't tear it. Like the classic example is a coffee mug being topologically the same as a donut. Figures are elementarily related or homeomorphic if they have the same sort of fundamental structure numbers. Specifically, the number of boundary curves, let's call it V-think edges or openings, and the genus per feet, basically the number of holes. A donut has a genus of 1. Riemann boiled this down to connectivity, which is just 2p plus v1. It's about the deep structure, not the surface shape.
Okay, this next part is fascinating. Geometry can transform points into entirely different things. Like a point becomes a line.
It sounds bizarre, but yes, a simple case is a polar relation. You start with a point in one plane, apply a rule like finding its polar with respect to a unit circle, and boom, it corresponds perfectly to a specific line in another plane. Point becomes line. And for a really surprising link to the real world, consider contact transformations, named by Sophus Lie. This is where super abstract math connects directly to mechanical engineering. These transformations are the mathematical theory behind how you design gear teeth.
No way. Gears.
Yes. The way one gear moves relative to another can be described precisely by a contact transformation. For two gears to mesh smoothly, the profiles of their teeth need to be curves that correspond to each other under such a transformation. Think of involute curves or cycloid curves used in gear design. Those shapes come right out of this theory, ensuring the teeth engage and transfer motion correctly.
That's incredible. Abstract math designing physical gears. So, connecting this back to the bigger picture, Klein emphasizes how fundamental things like vectors and scalars get their real definition not just from size and direction, but from how they behave under these geometric transformations. How does that deepen things?
It makes the definitions much more rigorous and consistent. Hamilton gave us the terms scalar and vector. A scalar, like temperature or mass, is basically invariant under coordinate changes, or maybe just changes by a simple factor. A vector, though, like displacement or force, is defined by its components and how those components change, how they transform when you change the coordinate system. Building on that, you get scalar fields, a scalar value at every point in space, like a temperature map, and vector fields, a vector at every point, like wind velocity or a magnetic field.
And there's a subtle difference between types of vectors, too. Polar and axial.
It's about how their components behave under reflection, like looking in a mirror. Polar vectors, like electric field strength, behave one way. Axial vectors, like magnetic field strength or angular velocity, behave slightly differently under reflection. It's a finer distinction, but important in physics.
It's interesting you mentioned the history of vector notation. There was that committee in Rome that tried to standardize it, but apparently they failed.
Yeah, that's a great historical footnote. The vector calculus we use today is kind of a mashup. It came mainly from two big sources, Hamilton's quaternion calculus and Grassmann's theory of extension. Grassmann's stuff was brilliant, but initially really hard to penetrate, so it languished a bit. Hamilton's ideas got picked up more in physics, especially by James Clerk Maxwell. Later on, folks like Oliver Heaviside and Josiah W. Gibbs, who started as Hamiltonians, actually integrated Grassmann's more flexible ideas, and that blend eventually became modern vector calculus. Klein's point through all this was that the principle of invariance, what stays the same under transformations, is the guiding star that helps make sense of all these different mathematical objects and notations.
Okay, now here's where it gets really interesting for me again. Klein argues that bringing imaginary numbers into geometry actually simplifies theorems and makes them more general. That feels completely backward. How does adding imaginary stuff make real geometry simpler?
It's a very elegant mathematical convention, actually. By allowing coordinates to be complex numbers, theorems often lose their exceptions. For example, the statement, a line and a conic section always intersect in 2 points. Without imaginary numbers, you have cases. Maybe they intersect twice, maybe once, tangent, maybe not at all if you only count real points. But if you allow complex coordinates, the statement becomes universally true. The 2 points are always there. They might just be complex, or they might be the same point counted twice, or they could be at infinity. No more awkward except when. Clauses. It provides consistency.
And wasn't there someone, von Stout, who found a way to actually visualize these imaginary points, to make them feel more real?
He did. It's quite ingenious. Von Stout showed that an imaginary point on a line can be represented uniquely by a pair of real points on that line, plus a direction, an arrow to distinguish between, say, plus I and I. It gives a concrete, geometric handle on something abstract. Similarly, concepts like the imaginary circular points at infinity or the imaginary spherical circle, these sound purely abstract, right? But they have real geometric counterparts through things like polar relationships and involutions, and using them dramatically simplifies theorems about circles and spheres in projective geometry.
So the takeaway isn't about finding some mystical meaning in imaginary numbers. It's more pragmatic.
Exactly. Klein wasn't looking for metaphysics here. He saw imaginary numbers and points at infinity as incredibly useful mathematical conventions. By adopting them, you create this complete, consistent geometric framework where theorems hold without annoying exceptions. It's about making the math work better, cleaner. It's a powerful tool for consistency.
Now, Klein's work isn't just advanced math theory. It's also a pretty strong statement about how we should teach geometry. And he had some bones to pick with traditional methods, especially Euclid.
Oh, absolutely. He respected Euclid's historical achievement, the logical structure. But from a modern viewpoint, he saw major shortcomings. For instance, Euclid didn't really have axioms for betweenness, the order of points on a line. And he treated all quantities like lengths and areas as absolute values without signs. This forced him into all these cumbersome distinctions of cases for theorems. Compare that to the modern cosine rule, c cogl plus b upol 2 ab cos gamma, where the sign of the cosine automatically handles whether the angle is acute or obtuse. One formula covers all cases, thanks to signed quantities implicitly being used.
And that lack of rigor opens the door for those tricky geometrical sophisms, right? Like the fake proof that all triangles are isosceles. They seem convincing until you look closely.
Precisely. Those sham proofs often rely on subtly inaccurate diagrams, or playing fast and loose with the order of points and lines, exploiting the gaps in Euclid's explicit axioms. The isosceles triangle one, for example, usually depends on drawing the intersection point of the angle bisector and the perpendicular bisector inside the triangle, when for most triangles it actually falls outside. It shows why relying purely on intuition and flawed diagrams isn't enough. You need rigorous axioms.
But Klein didn't just trash Euclid. He found things to admire too, didn't he? Something about an axiom?
Yes, he praised what's often called the Archimedean axiom, which likely came from Eudoxus but is in Euclid. It basically says that if you have two quantities of the same kind, say two lengths, you can always multiply the smaller one enough times to exceed the larger one. This sounds obvious, but it implicitly rules out actually infinitely small or actually infinitely large quantities. It anticipates the rigorous foundations of the real number system. So yeah, he saw sophistication there too.
So when it comes to actually building geometry from the ground up, Klein thought there wasn't just one single correct way. That seems pretty radical for the time.
It was quite forward-thinking. He outlined two main modern approaches. One starts with the idea of a group of motions, translations, rotations, and derives things like distance from that group structure. The other starts with axioms about congruence, how shapes are the same size and shape, and things like parallelism emerge later. But Klein's core belief was in the freedom to choose your starting axioms, as long as the resulting system is logical and consistent. He really pushed back against dogmatic attitudes, what he called intolerant utterances, claiming one specific concept was the only right foundation. He felt naive intuition gives us the raw material, we idealize it, and then logic takes over. But the initial choice of idealization has flexibility. And this philosophy really culminates in his famous Erlanger program from 1872. This program systematically classifies different geometries, metric, affine, projective, and so on, based on the group of transformations that leave their specific properties unchanged or invariant. The tool for this is invariant theory, which is all about finding mathematical expressions, invariants, involving coordinates and shape parameters that don't change when you apply the transformations of that geometry's group. Determinants are a basic example. He showed how you could view affine and metric geometry as special cases within projective geometry by adjoining certain elements, like adding the infinitely distant plane to get affine properties, or adding the imaginary spherical circle to get metric properties like distance and angles.
And this is where tensors pop up again. They come out of this classification.
Exactly. Tensors emerge naturally as objects whose components transform according to specific rules dictated by these transformation groups. They're fundamental geometric quantities arising from this invariant theory perspective, and hugely important in physics, elasticity, relativity, you name it.
So bringing this back to teaching, Klein was a huge advocate for that fusion idea in the classroom, mixing arithmetic and geometry, plane and solid geometry.
He was, and he highlighted reforms happening around Europe that were moving in that direction. In France, Legendre's geometry book from way back in 1794 had already tried to bring in more intuition and fusion. Later, Charles Murray's 1874 book built geometry rigorously from the motion group, integrating plane and solid from the start, adding axioms only as needed. The big French reform of 1902 really pushed modern ideas, like the function concept, into geometry teaching. In Italy, mathematicians like Cremona, Sagna, and Dovidio worked on replacing Euclid with more modern logical approaches, often based on motion or congruence axioms, and being careful about limit concepts. But Klein also shared a warning parable from Italy about logic versus intuition. There exists a limit beyond which even any possibility of life ends. You need both. In Germany, there was the influence of Pestalozzi's very intuitive approach, the Anfangslehre, which you still see echoes of in kindergarten methods. And figures like Holtzmüller pushed for integrating different math subjects, emphasizing practical drawing and building spatial intuition.
Klein also had some really interesting thoughts on mathematical ability, didn't he? Challenging the idea that only some people are math people.
Yes, that's a fascinating psychological insight he offered. He strongly challenged the notion that mathematical talent is rare. He blamed defective methods of mathematics teaching for creating that impression. He believed good teaching, tailored appropriately, could enable pretty much all students to learn mathematics successfully, assuming they put in the effort. He also observed different types of mathematical minds, some strong in abstract calculation, others in geometric intuition, some visual thinkers, some auditory. He suggested teaching should try to cater to these diverse strengths. It really puts the onus on pedagogy, not just innate ability.
And he even weighed in on the classic debate about construction tools in geometry.
Yeah.
Are we stuck with just ruler and compass?
He had a definite opinion on that. He argued forcefully against the traditional restriction. He basically said there's no valid reason to restrict ourselves to ruler and compass. Other tools, like an adjustable right-angle tool or even a flexible ruler for drawing arcs, are perfectly valid geometrically. He pointed out that different types of geometric problems naturally correspond to different tools. Projective constructions might only need a ruler. The famous Apollonius problem constructing circles tangent to three given circles belongs to a group involving scaling dilatations, which the compass can handle, but the point is the restriction itself isn't logically necessary. Ultimately, Klein's vision for math education was about providing a general orientation, an overall framework of geometry, in which all parts find a convenient place. He wanted students to see the connections, the big picture, moving away from studying subjects in isolation.
Wow. Okay, so we've covered a lot. From the basics of signed quantities giving universal formulas to the unifying power of transformations defining different geometries. We saw how abstract concepts like contact transformations surprisingly connect to real-world things like gears. And we challenged some deep-seated ideas about Euclid, how geometry should be founded, and even how it should be taught. It really underscores that understanding a subject means being willing to question its very foundations.
Absolutely. Klein's work is a powerful reminder that mathematics isn't static. It's not just about finding answers. It's about asking better questions, refining our frameworks, seeing hidden connections, and appreciating the larger landscape.
So here's something to think about. How might rethinking the very foundations of a subject, or challenging those rigid traditions Klein talked about, transform not just what you learn, but how you learn? How could that perspective unlock new possibilities, maybe even in fields far removed from mathematics?